Okay, so I'm having to refilm this because in class I didn't film it, which is great. Perfect waste of time. Going back through the beginning of chapter 4, which deals with alkanes and cycloalkanes, and specifically at the beginning of chapter 4, what we really deal with is kind of like nomenclature of alkanes, right? Number one, we have to introduce what alkanes are, right? So just as a note, alkanes are a type of hydrocarbon. Hydrocarbons essentially are compounds that only consist of carbon and hydrogen atoms. And here below I have listed a bunch of different types of hydrocarbons. So a nice example of one is ethane. We've got acetylene, and benzene. And so, again, all of these compounds, all they contain are carbon and hydrogen bonds. And so all of these compounds essentially constitute this idea or this class of molecules that are called hydrocarbons. Okay? Now, that's important, right? We have lots of different types of compounds that are considered hydrocarbons. But in this chapter, what we're really going to focus on are alkanes. Okay, so alkanes, a nice example of an alkane is given here, ethane, right? So ethane compared to ethylene and acetylene, ethane lacks something that's fairly important, right? So in ethylene, we have a carbon-carbon double bond. A double bond, just as a reminder, consists of a sigma bond. It has one sigma bond, but it also has a pi bond. Another type of bond is a triple bond. As a reminder, a triple bond is a sigma bond, and then it's two pi bonds, right? And then in this aromatic compound, so this benzene ring, this is aromatic, it is also a hydrocarbon, right? So all it has is carbon-hydrogen single bonds. Just as a reminder, there are implied hydrogens all around this compound. Please do not forget the implied hydrogens. They are there. But again, this guy also contains this alternating list of double, single. And again, because of that, these double bonds also consist of pi bonds, right? So we have this delocalized network of pi bonding in this aromatic ring. Right, so ethylene, acetylene, benzene, all of these guys contain pi bonds. It's the big takeaway here. Whereas our alkane, which is again going to be the first functional group that we deal with in this course, don't, right? So alkanes only consist of carbon-carbon and carbon-hydrogen single bonds. So big important thing there is it only consists of sigma bonds. There are no pi bonds in an alkane. No pi bonds, okay? Now, this entire chapter is going to deal with a lot of different things with respect to alkanes, right? So we really get introduced pretty hardcore into a lot of concepts in organic chemistry in this chapter. I do want to note that the alkanes, in terms of the functional groups, these are the simplest and most basic of all of the compounds that we're going to deal with, right? So we will hit really heavy on a bunch of new concepts, but this is essentially kind of like the simplest type of compound that we're going to deal with. So, big question, how do you know that you're dealing with an alkane? How do you know that you're dealing with only carbon, and carbon-hydrogen single bonds? So usually molecules that are alkanes end in ane, right? So propane, butane, pentane, these are all alkanes because, again, they have that ane ending. And we'll talk about how we'll be able to tell the difference or know that this is propane versus butane versus pentane as we get into naming in a second. Okay, so what we'll find in terms of organic chemistry long term is every time we introduce a functional group, right, so a new functional group and all of their reactions, etc., we always have to spend time learning how to name those compounds, right? And so at this point in time, we really haven't talked about naming or what we define as nomenclature in organic chemistry, right? So in general chemistry, we do go over nomenclature very briefly, right? So we talk about how to name things like sodium chloride, right? Or let's say hydrochloric acid, right? These guys have their own specific naming scheme. And again, the purpose of that is saying, okay, if I say, sodium chloride, I need to be able to know, given this name, right, what compound I'm actually dealing with, right? And so we go over all these rules about how, okay, well, type 1 metals, it's an ionic compound. If it's a metal and a non-metal, we know this is sodium chloride because this is a type 1 metal. It's very predictable, etc. It's all these rules that we talk about, okay? Same exact thing comes into play in terms of organic chemistry, but what's going to happen is it's going to get a lot more complex, because organic molecules in general are a lot more complex than just these basic formula units of ionic compounds or acids, etc. Right? So we have a lot of different nomenclature rules, so that we can essentially be able to take, let's say, a compound like octane, so C3H8, and we can say, okay, this is octane. We know this is octane, and I know the exact compound, the exact structure of this thing that I'm dealing with because of the way we've named it, right? So I could say, oh, octane. It's not octane. It's propane. Yeah, it's propane. I'm not going to stop. So again, we'll say C3H8. This is propane. And again, the entire purpose of this is saying, okay, I'm dealing with propane. I know that the structure of propane is something like this, right? That we can go from our bond line structure to the name and vice versa, okay? That's the purpose. Now, hopefully in the next little bit, I'll be able to provide you with a nice rationale behind why you would need this. So before there are any type of specific rules or set of rules in place with respect to organic nomenclature, people who synthesize new compounds or who isolated new compounds essentially just name those compounds on their own fancy, right, on their own whims, whatever they wanted to name them. And so I give an example of formic acid here. Formic acid is named formic acid because it was isolated originally from ants, and the Latin word for ants is formica, right? Same thing for urea. Urea was isolated from urine. That's why it gets its name, urea, right? Now, hopefully, you should be able to see that if I say formic acid and I say, hey, I'm dealing with formic acid, there is nothing in this name that would give me any indication, besides the acid part maybe, of what the actual structure of this compound is. Same thing for urea. There's nothing in this word, urea, that's going to give me any indication of what this overall structure is, right? So this is an issue. If we did something like this for all of the compounds that we ever had to deal with, then we would have to memorize the structure of everything given a name, which would be a huge hassle and something essentially that nobody wants to deal with, right? So the purpose of all of these rules that we're going to learn is how we can easily utilize this same set of systematic rules to produce a name for a compound that essentially we don't have to sit here and have to memorize for all the different compounds, okay? Okay, so that systematic set of rules that we utilize is something called the IUPAC system of chemical nomenclature. And we're going to get into what the kind of laws are, or the rules, how you guys are actually going to be able to name compounds given this IUPAC system. So IUPAC, I'm going to go ahead. In class, I wrote how to say this. I say it really quick, IUPAC, and people are like, oh, what is she saying? But phonetically, IUPAC is I, and then U, and then PAC, right? And all I'm doing is just saying I, U, PAC. This is an acronym. It's not anything special. It just stands for the International Union of Pure and Applied Chemistry. And essentially, it's these guys, this union, these people that lay out these rules for our chemical nomenclature, right? Okay, so first step in utilizing the IUPAC system of chemical nomenclature is to find what is called the parent chain. So here I've given you guys a nice alkane, right? Again, I know this is an alkane because all I see here are carbon-carbon single bonds and carbon-hydrogen single bonds, right? So please remember that there are implied hydrogens all over the entire structure when we draw these bond line structures, okay? Okay, so for alkanes, when we're naming alkanes, the parent chain is defined as the longest consecutive carbon chain, okay? So a lot of people always like to start on the left or on the right, right? And essentially just count 1, 2, 3, 4, 5, 6. That's not the longest chain though, right? If we instead said, okay, I'm going to start here, 1, 2, 3, 4, 5, 6, 7, 8, 9. That gives us 9 carbons, and again, those are all consecutive carbons. If I instead had said, okay, I'm going to start here, 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, 8. That guy would have given me 8. The longest chain still is going to be the one that gives us the 9, okay? So again, the parent chain here is the longest consecutive carbon chain, and that is the first step in our IUPAC system of chemical nomenclature, is you need to find the parent chain. So longest consecutive carbon chain, and the first step is finding that, okay? So we have done that here. So we have 9 carbons. This is our parent chain, and what I usually like to do to just kind of relieve any type of ambiguity is I like to go ahead and just snake my way through my parent chain so that I can set my parent chain off from everything else, okay? Now, first step is finding the parent chain. The second step is naming the parent chain, okay? And so because we are dealing with alkanes and we're learning how to name alkanes, all of our parent chain endings are going to end in A and E, right? So that's the first step. Now, the first part of this is going to deal with how many carbons are actually in our parent chain, right? And so we're going to name our parent chain based off of this set list of essentially carbon for prefixes for how many carbon atoms we have, right? So if our parent chain had only 1 carbon atom, then it would be called methane, right? If we have 2 carbon atoms, it's called ethane. 3 is prop. 4 is butane. 5 is pent. 6 is hexane. 7 is heptane. 8 is octane. 9 is nonane. 10 is decane. It is important to note at this point in time that you memorize these first 10 prefixes, these first 10 names of these parent chains, right? Everything past 10, there is a name for them, right? But we tend not to deal with anything greater than 10 carbon atoms at a time, right? So for the quiz, for exams, for homeworks, you need to probably memorize the first 10 of these. Past that, I wouldn't worry about any of these guys over here. Okay, so again, we're trying to name our parent chain, right? And again, it's going to depend on how many carbon atoms are in there. For that one that we just looked at, we had 9 carbon atoms. So the name for the carbon, or the parent chain for that, is nonane, right? Note that this 1, 2, 3, 4, all the way to 10, meth, eth, prop, but, pent, hex, hept, oct, non-dec, these guys are going to come back in a second, right? So these prefixes are going to essentially follow the same overall idea, right? 1 carbon is a meth, 2 carbon is an eth, 3 carbon is a prop, etc. Okay? When it applies to the parent chain, we end it in ane, so it becomes methane, ethane, propane, butane, etc. Okay, so now that seemed easy, right? With respect to that nonane molecule, there was like only one way to get the most carbons, right? There was only one way to get 9 carbons out of that. But sometimes you're going to have molecules where there's a tie, right? So for example, in this example right here, it's the same compound that we're looking at. This guy and this guy, they're the exact same compounds. But what we find here is that if we start over on the right, we get 1, 2, 3, 4, 5, 6, 7, right? So 7 carbon atoms. If instead we had branched and gone this way, we would also be left with 1, 2, 3, 4, 5, 6, 7, right? So it's the same compound. Depending on how we weave ourselves through this, we get the same exact number of carbon atoms. So essentially we have like a tie for who the parent chain is, right? Now, the way that we're going to break that tie is we're going to take the parent chain to be the one with the most substituents on it. Okay, and so a substituent is going to be anything that branches off this parent chain. So if we start over here on the left-hand side, so this guy, if this is our parent chain, then we'll note that we have 1, 2, 3 different branches off of it, right? So we have 3 different substituents here. Whereas if we started on this guy, if we went this way, same exact 7-carbon chain, we would only get 1, 2 substituents off it, right? So the purpose of this is determining who is the actual parent chain. Is it red or is it blue? And the answer to that is it's the one that gives you the most substituents, right? Red gave us 3 substituents, so we had 3 versus 2, right? So the parent chain is the one that's going to give you the most substituents, and so in this situation, it is this chain. Okay? So if there is a tie, which can happen, you're looking for the chain that gives you the most substituents. That is going to be your parent chain. And again, regardless, we're going to have 1, 2, 3, 4, 5, 6, 7. So this has 7 carbon atoms. So the prefix for 7 is hept. This is heptane as a parent chain. Okay, so sometimes our compounds, our alkanes, are going to have are going to be in like a ring type structure. So they're going to be in a cyclic ring type structure overall. We have to denote that in the name, right? So for example, earlier I had drawn propane. So I had said, oh, propane we knew was carbon 3, hydrogen 8. And I said, oh, this is propane. All right, so it has 3 carbons. This is propane. But let's say that we look at this guy over here on our left, and we find, oh, we have a cyclic base structure here, and we have 1, 2, 3 different vertices. So again, a vertex is a carbon. So this also would tell us this is 3 carbons. So if we were looking for a parent chain, oh, this is 3-carbon ring, and we would try to call this propane. But again, this guy and this guy are 2 different compounds, so 2 completely different things, right? So to essentially denote the fact that this is the cyclic ring structure, all we're going to do is we're going to add cyclo as a prefix to the beginning of the parent chain, right? So again, it's 3 carbons, so the parent is propane, but this is going to be called cyclopropane to denote the fact that it is a ring-based structure, right? So the parent chain, the parent name for this is cyclopropane. Same thing here. We've got 1, 2, 3, 4. So if we looked up on that chart, or if we memorized 4 carbons, the prefix for that is bute. So the parent chain here is butane. But again, this is a cyclic structure. It's a ring. So to denote that, we have to say cyclobutane. And then finally, we have this guy on the end. We've got 1, 2, 3, 4, 5. 5 carbons. The base of 5, or like the prefix for 5, is pent, right? So again, this would be pentane, but again, it's cyclic, so we have to say cyclopentane to name the parent for any of these guys. So we have cyclopropane, cyclobutane, and then cyclopentane. Okay, so I'm going to let you guys have some time to give this one a try. You're identifying and naming the parent chains of the following alkanes. And the only thing I want to note is that if you do have a ring, and let me maybe write this a little bit better. So if you do have a ring-based structure, it is usually going to be the parent chain, right? So if there is, let's say, if I drew my nice cyclobutane, and then off of it I drew a substituent, right? This guy is our parent chain, and this just counts as a substituent off of it, right? So the parent here would be cyclobutane, and then this thing doesn't get counted as the parent chain. So this guy doesn't get counted, it just gets counted as a substituent, okay? Okay, so go ahead and try this. What I'm going to suggest for these guys is that you pause the video and then come back and I will share the answers with you once you restart. Okay, so hopefully you guys took some time with these. We did them in class, but just as a reminder. So I'm going to start up with this guy at the top. Again, we're looking for the parent chains in each of these alkanes, looking at the bond line structure. And so for this guy, I'm going to start over here on my left. So any endpoint or vertices of carbon, we've got 1, 2, 3, 4, 5. And then if I go down here, let's say we have 5, 6, 7. That would give me 7. If I kept going on that original chain, we have 5, 6, 7, 8. This guy would give me 8. Again, I don't think there's any other way to get more than 8. So this guy here, 8, is my parent chain. Just as a note, you could have, instead of going out to this guy, you could have said 7 and gone down to this guy and gotten 8 as well. They are essentially the same exact compound, right? So it doesn't matter if you pick this one or if you pick this one, you're only going to get 8. And once we start naming and talking about substituents, then it's going to be a little bit more clear how either or doesn't matter. It's the same compound regardless. So 8 is the parent chain. And again, I'm going to go ahead and just circle this guy so that I don't confuse myself. And then the base for 8 is oct. And so the name of this guy is octane as a parent chain. Okay, so same thing down here. I'm going to start up here on the top. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. It's kind of boring. It's going to give you the same exact thing. If I had started down here, I'd get 1, 2, 3, 4, 5, 6, 7, 5, 6, 7. Doesn't matter if I'd gone up or down for that guy. So again, we're going to get 1, 2, 3, 4, 5, 6, 7, 8. 8 is our parent chain here. And 8 again is octane. And now, last one, we've got kind of a jellyfish looking thing here. We do have a cyclic structure, and I did say if you have a ring, the ring is its own like self-contained thing. It's not going to like branch out any farther. And so we do have a ring here. We have 1, 2, 3, 4, 5, 6, 7, right? The ring is going to be the parent usually, right? As long as a branch off of it isn't longer. So the longest branch that we have off of our ring here is this guy. We've got 1, 2, 3, 4. 4 is not longer than 7. So our ring is our parent, and I'm going to go out here. A ring is our parent. So 7, the base for 7 is hept. And again, it's an alkane, so heptane. But because it's a ring, we have to specify that by putting in the cyclo prefix. So this is cycloheptane as our parent chain. Okay, so that was step 1. Rule number 1 was to determine or find the parent chain of the compound and then determine its overall name, okay? So in step 2, there are going to be 4 of these steps or 4 of these like kind of basic rules that we're going to follow. We're going to identify and name all the substituents off of the parent chain, right? So for example, let's say we were dealing with this molecule and we had followed step 1. So we'd gone in, we'd found, okay, well, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? That's the longest consecutive branches of carbon, longest carbon chain here. So 10 has that last base. This is going to be a decane as a parent, okay? Now, that is a parent chain. We have things that come off of the parent chain, though. So, for example, right here, we have a substituent, a branch off of this that has one carbon, right? So it's got one carbon right here, and it has two carbons, right? Down here we've got a branch that comes off that has 1, 2, 3 carbons, and here we've got a branch that comes off that only has one carbon, right? So these are what we call substituents, right? And we're going to name them depending on, again, on how many carbons they have. So if we only have one carbon, then that base for one is meth. But because it's a substituent as opposed to part of the parent, instead of ending it in A and E as a substituent, we're going to instead change that to YL. So this becomes methyl. Up here, this guy has 1, 2. So the base for 2 carbons is F. But because, again, this is a substituent, this becomes ethyl. And then down here, we've got 1, 2, 3 carbons as a substituent. The base for 3 carbons is prop, but because it's a substituent, we name this propyl, right? So essentially, we replace that A and E for substituents with YL. So for this guy, we've got decane as our parent, and then we've got a methyl, we've got an ethyl, and we've got a propyl substituent. Now, those are easy because the substituents aren't very complex. They're just chains of carbon themselves. We're going to find, though, that those can get a little bit more complex. And then I did mention this when we went over the question just a second ago. So usually, if you do have a cyclic structure, if you do have a ring, that will be your parent. The only exception to that is if the branch off of the ring is actually larger than the ring itself, right? So for example, this problem, our ring here has 1, 2, 3, 4, 5, 6. So our ring has 6 carbons, and then it has a substituent off of it. That substituent only has 1. So we have 1, 2, 3. Our substituent only has 3 carbons. So for this guy, we would consider this a 6-carbon parent. 6 is hex. This is hexane, and again, because it's a ring, it's cyclohexane. And then we have a 3-carbon substituent here. So 3 carbons is prop. So this would be a propyl group. Okay, so propyl, and then the cyclohexane as the parent. Now again, this was our parent because it has 6 carbons. And usually if you have a ring, that is going to be the parent. But in this example below, we have a ring that only has 1, 2, 3 carbons, and we have a branch off of that ring that has 1, 2, 3, 4. So here, the actual parent is this 4-carbon chain. So 4 carbons is meth, eth, prop, bute. So our parent here is butane. It's not cyclo because this is not the ring structure. The substituent now is this guy. This guy has 1, 2, 3, right? So 3 is prop. It's a propyl because it's a substituent, but now we also have to specify that it's a cyclic ring structure because this and this are not the same thing, right? We have to say that. So to specify that in naming the substituent, we would also just include cyclo in front of it. All right, so in this one, our parent is butane and our substituent is cyclopropyl. Okay, so those were all kind of, I mean, I'm not going to say they were easy, but again, they didn't get very complex, right? We had a parent chain, it was identifiable, and then all of the substituents that came off of it were just, just individual chains of carbon, okay? I'll try to, make sense of that here. So sometimes we're going to have what's called complex substituents. So for example, in this guy, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Ooh, I don't ever remember what 11 carbons are. So this 11 carbon chain, this is our parent, right? So 11 carbons, I think, is undecane. So we've gone ahead, we've done step number 1, we've identified the parent. Now we're going to look at and identify our substituent, and we'll notice in our substituent, we've got 1 So we've got 1, 2, 3, 4, but then this substituent itself has another branch off of it, like a substituent on a substituent, right? And that gives us 5 carbons overall. So our substituent here has 5 carbons, and you would be tempted to say, well, 5 carbons, that's pent, so I'm just going to call this a pentyl group, right, as my substituent. The problem with that, though, is that pentyl is actually that just continuous chain of carbons, right? So a pentyl group would look something like this, where we have 1, 2, 3, 4, 5, and that is not what we have over here, right? So this is what is called a complex substituent, where we have a substituent, this guy, that has branched off another substituent, okay? Now, how are we going to go about naming this? So what's going to happen is we're essentially going to treat the substituent as its own little parent chain, right? And so in this, we'll find that if we just imagine that this isn't attached to anything, we're just looking at it by itself, that if we're looking for a parent chain in this little mini group, we would look for, again, the longest carbon chain. And we'll find that we have 1, 2, 3, 4, and that is the longest carbon chain, okay? So that's going to be like our new mini parent. It's still a substituent, so we still have to name it so. So a 4 group is a but. This is going to be a butyl. And now what we're going to do is we're going to number it, and we're going to number it starting with this carbon that's directly attached to the real parent, getting the number 1, and then we're going to number sequentially afterwards. So this goes 1, 2, 3, 4, okay? Now, we've identified that the butyl is kind of like our mini parent. Now, from butyl, we only have one thing that branches off of this, and this is a 1 carbon chain, so this is a methyl group. So now, to denote that in the name, what we need to say is where that methyl group is on our new butyl group, right? And so that's why we have numbered these guys. We have 1, 2, 3, 4. This methyl group branches off of our butyl group at the 2 position. So to identify that, we're going to put that out front, and we're going to separate that via a dash. So this is 2-methyl, and then butyl. Okay, so as a complex substituent, this thing is called 2-methyl-butyl. Again, the 2 is telling us where that methyl group branches off the butyl chain. That's what it's trying to imply, essentially. And just as a note, we'll get into this a little bit more later. Anytime we have a number and we separate it from a letter, we always use a hyphen to do that. Okay, so that's kind of more difficult, right? Identifying and naming those types of substituents. So we have a couple of these guys that are actually fairly commonly used quite a bit. And they have common names that we're allowed to use in our IUPAC nomenclature. So instead of having to go through and name these complex substituents that we see quite a bit, we are allowed to utilize their common names. Okay, so I'm going to go through those common names that we are allowed to use, that you should use and you should memorize. And then we'll get some practice actually naming our substituents, okay? So there are going to be 3 sets of them, depending on how many carbons are in each of our various substituents. The first one we start with is propyl. So this is a complex substituent that has 3 carbons in it. And there's essentially only one way that we can branch that to get a complex substituent. It's essentially taking this guy off the end and branching it at this position, right? And so what we end up with is this guy. Sorry. So if we had to try to go about naming this guy as a complex substituent, we would, again, look for our little mini parent chain. So that has 1 carbon, 2 carbons. And then we have a methyl group that branches at the 1, 2 position. So it branches at the 1 position. So this guy would be called 1-methyl-ethyl. 1-methyl-ethyl. Again, that's a hassle. Nobody likes to do that. This is also just known as isopropyl. Okay? So if you look at this and you look at it from the side, to me, this looks like a Y. a Y shape. And that Y shape we're going to see as we move through this is kind of characteristic of this iso group, right? So this is iso and then propyl. It's isopropyl because, again, there's only 1, 2, 3 carbons in it. So isopropyl. Isopropyl, again, if you wanted the real complex name, it's 1-methylethyl. Okay, so that's the only 3-carbon complex substituent. For 4 carbons, we get a couple of them. So 4 carbons, the butyl group. There are a couple different ways that we can branch that. So the first one, we can take, let's say, this methyl group out here, and we could branch it at this position. So here we'd be left with something that looks like this. I'm going to come back to this one because this is the one that I never remember. I remember all the other ones, and then I leave sec-butyl as like an afterthought. Another way that we could do that is we could branch it, take this guy, and we could branch it at this position. Sorry, sec-butyl is branching here. So we could take it, we can make this guy with it, right? So again, this looks like a Y to me. It looks like a Y with an elbow at this point in time. So that Y is very characteristic of the iso group, but because this guy has 1, 2, 3, 4 carbons in it, then this is known as the isobutyl group, as opposed to the isopropyl, which just had 3 carbons. And then another way that we could branch it is by branching them all at that first carbon, right? So we could have 1, 2, 3 methyl groups branched at that first carbon. This to me looks like a chicken foot, right? So I've always seen this and said, oh, that's a chicken foot. And I've just memorized the fact that the chicken foot is what we call a tert-butyl group. So chicken foot, tert-butyl, you can commit those guys to memory, right? Okay, so again, the purpose of doing this is the actual complex name for tert-butyl is 1,1-dimethylethyl. That's a hassle. Nobody likes that. It's easier to note that, oh, this is tert-butyl. Look, it looks like a chicken foot. And you can use tert-butyl to name it. You don't have to go through and say, oh, it's 1,1-dimethylethyl. So we've got isobutyl, we've got tert-butyl, and then the only other way that we could branch this guy is this one. We have 1, 2, 3, 4. It kind of looks like a hand, like a claw, but it's not always drawn like that, so that's why I don't want to think of a claw and know it's sec-butyl. Instead, what I would say is it has 1, 2, 3, 4 carbons. It's not iso, it's not tert, so it has to be sec. All right, so again, we're getting a branch off of that one position. The real complex name is 1-methylpropyl. So for these guys, memorize them. That's all I'm telling you to do. Memorize that this group is an isopropyl, this group is a sec-butyl, isobutyl, and tert-butyl. And then finally, we have only 2 to know for 5 carbons. So 5-carbon chain is a pentyl group. 1, 2, 3, 4, 5. There's 2 ways that we could branch that, or 2 ways that at least we tell you to memorize with respect to how we could branch it. So we could have our nice iso group again. We get the Y. Now we have like an elbow here as well as a shoulder, I guess, joint, if you want to look at it like that. And again, it has 5 carbons in it. It forms that Y shape. So this is 1, 2, 3, 4, 5. This is isopentyl. You can also call this isoamyl. Both of those are acceptable. And then finally, the only other one that we tell you to memorize is 1, 2, 3, 4, 5, another pentyl group. Now, instead of a chicken foot, this looks like a chicken leg. So I think now we have a knee cap here as well as a foot. So this is a chicken leg. And you should just memorize that chicken leg is a neopentyl group. Neopentyl. Of all of them, I would say that the butyls are probably the most utilized. Sec-butyl, isobutyl, isopropyl is very highly utilized, and then the tert-butyl is very highly utilized. We don't see as much with respect to the pentyls, but again, I've told you to know these, so you should probably know them. Okay, so go ahead and take a shot at this one. I've got 4 different compounds here, and I want you to identify the parent chain, number 1, and then I want you to identify and label all of the substituents and name them off of the parent chain. All right, so go ahead, give this a try. Pause the video, and then restart to get the answers to this. Okay, so we'll go ahead and go over these. Okay, so first step in answering any type of problem like this is to determine who the parent is. With the parent, we can then determine who the substituents are. So I'm going to start up here with this guy. So we're looking for the longest chain of carbon atoms. If we start over here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. If we had kept going, we had 1, 2, 3, 4, 5, 6, 7, 8. So 9 seems to be the longest. So let's go ahead. Let me highlight those because it makes it clear for me. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go ahead and circle it to identify the parent chain. And the circling, the reason why I do this is it also helps me identify who the substituents are. Okay, so 9 as a parent chain, the prefix for 9 is non. And so as a parent, this is nonane. And then the purpose of this was to identify the substituents as well as name them. And so once we have the parent chain identified, we can also look at the substituents. The first guy here, the only branch that we have is a single carbon chain, essentially, so just one carbon. So we know that one carbon is meth. And again, because this is a substituent, it's not methane, it's instead methyl, YL. And then over here, we've got 1, 2, 3 carbons. There's no complex branching here, it's just a straight chain of 3 carbons. And so because of that 3 carbon, 3, the base is prop. And again, because this is a substituent, this is a propyl group. So we have 2 substituents here. We have a methyl group and we have a propyl group. And again, the parent with a nonane. Okay, so moving over to the right, we've got a couple of choices here. So first off, we have a ring structure, right? We have a 1, 2, 3, 4 carbon ring. So we'll go ahead and identify that, 4 carbons. But then if we look off, we have a branch off of that chain or that ring. And that branch has 1, 2, 3, 4, 5 carbons, right? So again, usually the ring is our parent, except if the chain that comes off the ring is longer. And in this case, the chain that comes off the ring is longer. So this is 5 carbons. And so this is our parent, all right? It's a nice straight chain of 5 carbons. So this guy is called pent and then ane because this is our parent. And then this guy, our ring, is actually going to be our only substituent here, right? So 4 carbons, number 1, 4 is a but group, right? It's a substituent, so it's a butyl, but it's also a ring, right? So it's also cyclic structure, so this is cyclobutyl. So we have our parent, and then this is our substituent. It's our 1 substituent cyclobutyl group. Okay, so then moving on to this guy, what do we have here? We've got 1, 2, I like my highlighter, 1, 2, 3, 4. We go 5, 6, 7. 1, 2, 3, 4, 5, 6. Yeah, so it looks like 7 is the best. So we'll go ahead and say 1, 2, 3, 4, 5, 6, 7. That is our parent. So go ahead and circle that as our parent. So this is 7. And as a parent, 7 is hept. And then ane. And then we only have 1 substituent, but it is a complex substituent, right? So here, if we wanted to try to name this via its actual systematic name, we would we'd look for the longest chain. So we'd say that's 1 and 2. So 2 is an ethyl. Let's actually move that. There's not going to be any room for that. So 2 is an ethyl group, right? But then we have a methyl and a methyl branching off of it, right? So we would say this is 1, 2. We have 2 methyls, so we'd use a prefix called di. So this would be dimethyl. So this would be 1,1-dimethyl ethyl, right? Which is sucky and terrible. Nobody likes that. So hopefully, seeing that this name 1,1-dimethyl ethyl is terrible to look at and even try to name, hopefully you see instead, well, you know what that reminds me of? That reminds me of a chicken foot. And so hopefully you would realize that this is a common complex substituent that we use quite a bit, so it has a common name as well. So instead of having to go through this and say, oh, it's 1,1-dimethyl ethyl, you would say, oh, chicken foot, that's tert-butyl. And you would just know that because you would have memorized it, okay? Either or, you can choose. I would go with tert-butyl. So again, the parent here is heptane, and we have one substituent. It's this complex substituent, which is a tert-butyl group. Okay, so finally, we get down to the bottom one. This one's kind of difficult, and I've kind of ran out of room for it. So we've got a bunch of stuff going on here. Again, we're looking for a parent first. And where I would always start is probably the ring structure. So 1, 2, 3, 4, 5, 6. I don't know how I did that, but yeah. So it's 6 carbons. So that's going to start. If I look for anything that's longer than that on these branches, so if I go, okay, we've got 1, 2, 3, no. We've got 1, 2, no. We've got 1, 2, 3, no. 1, 2, 3, no. All right, so nothing's ever going to be longer than that 6-carbon chain. So that 6-carbon chain is going to be our parent. And it's 6 carbons, so it's hex. So hex. And then ane. But then again, it's a ring, so we have to say cyclo in front. So cyclohexane. And there is no space between these. These guys just run into each other. So cyclohexane. Okay, so that's our parent. Therefore, I'm going to go ahead and just circle it. We've got a lot of complex substituents that branch off this. This is supposed to be kind of like a little, test your new learned skills type thing. All of these complex substituents are these common ones that have these common names. So we shouldn't have to go through and have to say, oh, 1,1-dimethyl ethyl. Instead, we should hopefully be able to recognize them, identifying their common name. All right, so first one that I see are the Ys, because Y always just sticks out in my mind. So I have a Y here, I have a Y here. This Y has 1, 2, 3 carbons in it, so I know that Y is iso, and then because it has 3 carbons, it's isopropyl. Whereas up here, this Y has 1, 2, 3, 4 carbons in it, so it's a Y again. I can identify that it's iso, but now because it's 4 carbons, it's isobutyl. If we go down here, we've got our nice chicken foot, but it's not just a foot now, it's also a leg because it has a knee. So I know that it's a pentyl group. There are 5 carbons, and I just have to know that that chicken leg is called neo. So this is neopentyl. And then over here, we again are back to 1, 2, 3, 4. So this is one of our butyl complex substituents. It's not an iso. There's no Y. It's also not a tert. There's no chicken foot. So this is the only other one that you guys have to kind of know. So this is the odd one. This is the sec-butyl. And you can kind of see it. It's like again, like a claw about to grab something. Something like that. I don't know. You make it up in your mind. Okay, so we had a parent. Our parent was cyclohexane. That's awesome. Parent was cyclohexane. And then we had 4 different substituents. We had a neopentyl group, we had an isopropyl, we had an isobutyl, and we had a sec-butyl. Lots of different things going on here. Okay, so we've gone through the first 2 rules, or the first 2 kind of like steps in determining the IUPAC name for a compound. And so now we're going to start talking about the third step. So the third step, what we're going to do is essentially we're going to assign a number, or what we call a locant, to each position in the parent chain. And the main purpose of this is essentially to denote where the substituents come off of the parent chain. And so to do that, we do that with numbers, okay? So for example, we have two molecules here, right? So this first molecule is this methylpentane. It has a methyl group off of a parent chain that has 1, 2, 3, 4, 5. So this parent chain is pentane, and we have a methyl group as a substituent coming off, right? So if we look over to the right, we have a very similar thing. Again, we have a parent chain of 1, 2, 3, 4, 5. So we have a parent chain of pentane. And again, we have a methyl group coming off as a substituent, okay? So these guys are constitutional isomers. Both of them have the same molecular formula. So these are constitutional isomers. But they are not the same compound, right? And so if I had just said methylpentane and I had given you no other indication of where that substituent came off of the parent chain, then you wouldn't know if you were dealing with this guy versus this guy, even though these are two different compounds, okay? So the purpose of numbering the chain is to specify where these substituents are coming off. And again, those numbers is what we call a locant, okay? So I'll refer to locant. I'm talking about numbering the chain specifically. Okay, so then the question is, well, how do we number the chain? So there are a couple of guidelines that we're going to follow on how to know how to number the chain. The first one, though, is the fact that you're always going to start numbering from the outer carbon in. Okay, so the first carbon in the parent chain is always going to be carbon 1, and then the last carbon in the parent chain will be whatever number it is. Now, the big difference is, how do you know to start numbering, let's say, on the left end of the parent chain versus the right end of the parent chain? And so the answer to that is we're going to start numbering so that we can give our first substituent the lowest number possible, right? So again, this guy, this compound here, is the exact same compound. We have two options for how we're going to number our parent chain. Our parent chain is 1, 2, 3, 4, 5, 6, 7 carbons long. So our parent chain is heptane. And we could start numbering it here, or we could start numbering it here. Those are those are essentially the two options that we're considering. We're going to start numbering it, though, in whatever position is going to give our first substituent the lowest number possible. So if I started over here on the right, and I numbered 1, 2, 3, 4, 5, and I got to 6, whereas my first substituent here would be number 6. Whereas if I started numbering over here on the left-hand side of this carbon, or the left-hand side of this molecule, and numbered 1, 2, 3, 4, 5, 6, 7, all the way to the end, then my first substituent is at the 2 position, okay? So this is how we're going to number this chain, because it gives our first substituent the lowest number possible. Okay, and so this one's kind of easy because there's only one substituent. What about if we had more substituents, right? So let's say that we had this molecule down here. And again, this is the same compound that we're looking at. We are just kind of contrasting the two possible ways with which we could number the parent chain. So we could start over here on the left, or we could start over here on the right. And we're trying to figure out, well, which way is the correct way to actually number this. So if I started over here on the left, I would reach my first substituent, which is a methyl group at the 2 position, right? If I instead had started over here on the right, I would reach my first substituent at the 3 position. And again, we're going to want to number this so that the first substituent gets the lowest number possible. So right now we have this competition between 2 and this competition between 3. 2 is the lowest number possible, so this is the correct way to number the chain. It'll be 1, 2, 3, 4, 5, 6, 7, not this guy, okay? And so our second substituent here is going to be at the 5 position, as well as our third substituent at the 5 position. So when we start to assemble this, we would be listing these guys as 2, 5, 5, and not the opposite, or not this guy, which would have been 3, 3, 6. Okay, so again, we want to give our first substituent the lowest number possible. So now, what if there is a tie at the first substituent position, right? So let's say that, again, we're comparing the two possible ways to assign locates in our chain. Over here on the right, we start on the right, numbering 1, 2, 3, 4, 5, 6, 7. Over here on the left, we start on the right. We started at the left, pardon me. But over here on the right, we'll start 1, 2, 3, 4, 5, 6, 7, okay? So this is the question, right? Which was the correct way to number this? So for both of them, our first substituent comes at the 2 position and at the 2 position, right? So that's not going to tell us anything because the first substituent gets the same number, right? So if that's the case, where you have a tie in the first position, then you're going to move to the second position. And you want the second substituent to get the lowest number possible. So since the first position can't tell us anything, we move on to the second substituent. For the guy on the left, we get a 3, versus the guy on the right, we get a 5. So 3 versus 5. 3 is the lowest number comparatively. So this is the correct way to number this chain. So we will start over here on the right. This is 1, 2, 3, 4, 5, 6, 7. And that's how we would actually go about numbering this, okay? Now, let's say that you had a tie also in the second position. If that was the case, then you'd move on to the third position. If you still get a tie at that point in time, then you're going to give the substituent that has the lowest alphabetical order the lowest number possible. And I'll try to explain what I mean by that. So for example, here, in this bottom problem, we have a parent chain that starts here at a carbon, okay? So this is a bond between carbon and chlorine. When we're numbering the parent, though, or when we're counting parent, we're not counting any other atom besides carbon. So this is where this parent would start, this first carbon right here. We would then move on to 1, 2, 3, 4, 5. So our parent chain here is 5 carbons. 5 carbons, which is a pentane. And so then again, we have the same exact molecule over here. We have 1, 2, 3, 4, 5. And the question we're asking is, do we start numbering over here at the 1 or do we start numbering over here at the 1? Okay. Now, again, using our kind of what we've learned thus far, our first substituent is bromine, and I should mention this at this point. You will need to know how to name the halogens as a substituent, right? So I'm going to go ahead and write them, halogens. So bromine is listed here. Its name as a substituent is bromo. We also have a chlorine here. Chlorine's name as a substituent is chloro. This is going to be like your methyl, ethyl, etc. Fluorine, another halogen, is fluoro. And then for iodine, it is iodo. So that's how you would name these halogens as substituents, okay? Okay, so again, coming back here, if we wanted to figure out, okay, well, do we start at 1 or do we start at 1 here? We're going to look at where our first substituent comes. So on this guy right here, we've got bromo at the 1 position. On this guy, we've got chloro at the 1 position, right? So there's a tie for our first substituent. We then go out to the second substituent. For this guy, our second substituent comes at the 5 position. And for this guy, our second substituent comes at the 5 position, right? So right now, it's 1 versus 5 versus 1, 5. So we still don't know, like we have a tie for both of our substituents. So now the thing that's going to break that tie is we're going to give the substituent that comes first in the alphabet, we're going to give it the lowest number. So bromo is first in the alphabet before chloro. B comes before C. So the bromo is going to get, or the bromine is going to get the lowest number possible. So we would correctly number this chain 1, 2, 3, 4, and 5, and not the opposite. Because again, we're going to give bromine the lowest number possible because it comes first in the alphabet. Okay, so that is numbering. That's kind of the step number 3. We're going to assign numbers to the parent chain to identify where our substituents are at. And again, the way we're going to know is we're going to assign our first substituent the lowest number possible. If there's a tie, then we're going to assign the second substituent the lowest number possible. And if it continues on in this tie, then the substituent that comes first in the alphabet is going to get the lowest number possible. Okay, and then last thing with respect to numbering, anytime we're dealing with a cyclo, so anytime we're dealing with a cyclic ring-based structure, we're going to start numbering at the first substituent. So wherever the first substituent is, that's going to get the first number. So for example, if we had this molecule over here, we have a couple substituents. We have 1, 2, 3 methyl groups, 1, 2, 3 methyl groups. So our option here is to start numbering over here at 1. So we have 1, 2, 3. We could also start on the opposite side of the other first substituent, which is 1, 2, 3. All right. So now, if I did this guy, our substituents would be listed as 1, 1, 3, because we have 1 and 1 both at the 1 position, these 2 methyl groups, and then the third methyl group is at the 3 position. Or if I started over here, it would be 1, 3, 3. So again, the thing that's going to break the tie here is that second substituent. We want to give it the lowest number possible. So this guy is going to be how we're going to number the chain. Again, though, if it was just kind of a plain cyclohexane, let's say with just one group, then we would just say that this is the 1 position. Okay, so now we're going to start to bring stuff together. So again, first step was identifying the parent. Second step was identifying the substituents. Third step was numbering the chain to assign the parent a locant or individual locants. And now we're going to start to assemble. So the fourth step in this is to assemble. Okay, so to kind of illustrate this, we're going to use this cyclohexane as an example. So again, if I follow all of my rules, my first step is to find the parent. So for this guy, we have 1, 2, 3, 4, 5, 6. We have a parent that has 6 carbons. So this is number 1. So 6 carbons is hex, and since it's a parent, it's hexane. But because it is cyclic, it is going to have that prefix of cyclo. So this is cyclohexane. Second step is to identify my substituents. So I have a 1 carbon chain coming off my parent. I have another 1 carbon chain and another 1 carbon chain. So all of these guys are methyl groups. So methyl, methyl, and methyl. So now, after I've identified my substituents, I'm going to go ahead and number the chain to give them their locants. So that's step 3. We're going to number. And again, we just talked about this one. If I start over here, I'm going to give my substituents 1, 1, 3. So 1, 2, 3. As opposed to if I had started over here, we would have had a 1, 3, 3. So this guy was the correct way to number because, again, it gave that second substituent the lowest number possible. So we'll go ahead and use that guy, and I'll go ahead and erase these guys. Okay, so that's where we're at, right? So now we're going to assemble everything. And the first step that I want to mention in assembling everything is the first thing that's going to come in the name is the locants, right? So the locants are going to specify where our substituents are at. It's then going to be followed by our substituents, which is then going to end with our parent, okay? Now, for these guys, we only have one type of substituent. All the 3 substituents are methyl groups, okay? And specifically, there are 3 of them. So we're going to first, because they're all methyl, we get to clump them together. We're going to first start with our locants, right? So anytime we separate a number from a number, we utilize a comma when we start to assemble the full name. So first thing first, we have locants. Again, those are all numbers, so we're gonna separate them via comma. Now, anytime that we have a number separated from a letter, we're gonna use a hyphen, right? So a hyphen comes in, we have a number and we're separating it from a letter. So first things first, we have our locants, where they're at. We then follow that with our substituents. So we're going to specify what type of substituent it is. So we have 1,1,3-methyl. But now if we have more than one of the same type, then we need to utilize a prefix to specify that. So right now we have 3 methyl groups. And to say that we have 3 methyl groups, we're going to use the prefix tri. So di, as a reminder, is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, etc. Okay? So I have to specify that there are 3 methyl groups. So I will say tri-methyl. Those are all of my substituents. I have listed where they're at. So now I'm going to follow that with the parent. And so our parent here is cyclohexane. There is no dash here. There is no space. Those substituents are just going to move into the parent. And so this is cyclohexane. Okay, so that's kind of taking everything, putting it together. Unfortunately, this is kind of an easy one because all of our substituents are the same. So then there's only going to be one other thing that we need to mention before we can really start to utilize these. And it's what happens when these substituents aren't the same. Okay, so utilize this guy as an example of this. Okay, so we're going to follow our 4 basic steps, which is parent, substituents, numbering the chain, and then assembling the entire name. First step here, we're going to find our parent chain, which is the longest chain of consecutive carbons. I could start down here at the bottom. All right, so let's say I start here, 1, 2, 3, 4, 5, 6, 7. This guy would give me 7 carbons as a parent. Again, though, usually it's not going to be that nice and laid out. So let's say that I started up here instead. And I have 1, 2, 3, 4, 5, 6, 7, 8. This guy's going to give me 8. So that's larger. That's longer than 7. And then again, if I look for a different way, I don't think I could find anything that would give me more than 8 carbons. So 8 is going to be my parent, and I'll go ahead and circle it to kind of just cut it off from all the other substituents, just so that I can remind myself. So 8 carbons is octane as a parent. And so our first step is done. We've identified the parent, which is octane. Okay, so then second step, we're looking for our substituents. If I go through this, I've got a 1 carbon chain coming here. I've got a 1 carbon chain coming here. And then I've got a 1, 2 carbon coming here. So a 1 carbon chain is a methyl group. We can go ahead and write that. We've got a methyl. We've got a methyl. And then over here, we've got a 1, 2. 2 carbons is eth. And then as a substituent, it's ethyl. Okay, so I've identified the substituents. Now we need to number. I have 2 options here. I could either start over here at 1, or I could start over here at 1. Okay, so hopefully you guys can see that if I started over here at 1, and then went 2, 3, 4, 5, my first substituent comes at the 5 position, whereas if I start over here at 1, my first substituent comes at the 2 position. So this guy is the correct numbering scheme. We have 1, 2, 3, 4, 5, 6, 7, 8. So that's numbering, that's assigning the locants. Now we're ready to assemble. Okay, so again, it's going to come locant, substituent. But now for this one, we have 2 different types of substituents. We have a methyl group, we have 2 of them, and then we have 1 ethyl group. Okay, so To specify that, what we're going to do is we're going to list the substituents in alphabetical order. So as we start to assemble alphabetical order, we're going to start with the substituent that comes first in the alphabet. And for this guy, E, I don't know why it keeps doing this. E comes before M. And so we're going to utilize E. E comes first, so the ethyl group we're going to list first. So again, we're going to start first with the locant, where it's at. So we have locant first. The ethyl group is at the 4 position. So it's 4. Again, I have to state what group I'm talking about. So I have a number. It's followed by a letter. So this is 4 ethyl. I then have a cluster. I have 2 methyl groups, right? So because I have 2 of them, because there are 2 of them, I have to use that prefix di. So then I also have to state where they're at. So I have a 2, 3. So again, anytime I have a letter separated from a number, I use a hyphen. So it's 4 ethyl dash 2, 3 dimethyl. And then I end it finally with our parent. So it's locant, substituent, and then parent chain, which is octane. So really quickly, note that I only used ethyl and methyl as my numbering. I didn't use the prefix di, right? So we do not use these prefixes when we're alphabetizing. The only ones we do use to alphabetize are anything that has an iso. I hate this thing. Or anything that has a cyclo, right? So if we utilize things with tert or sec-butyl or any of those guys, we don't use these to alphabetize, but we will use, if you do have an iso prefix or if you do have a cyclo prefix, we will use those as to help us alphabetize. So I would identify, or I would alphabetize isopropyl, if I spell it correctly. If I had an isopropyl group, I would alphabetize it as I, not as P. But if I had a tert-butyl group, then I would alphabetize it as a B, not a T. Okay, so anytime we have one of these guys with a hyphen in it, we don't use that prefix to alphabetize. Okay, so with that, you guys do some on your own. So I have a lot of practice problems here. We're going to go through them. I'm going to spend some time with them because nomenclature is kind of important. So what I would suggest here is go ahead and pausing the video, trying to name these 2, and then come back for the answers. Okay, so hopefully you guys gave this a little bit of time to work through these. So go ahead and go through the answers. Starting with the molecule on the left. So again, the first step in doing this is identifying the parent chain. So go ahead and write that down. We've got number 1, we're looking for the parent. Again, the parent is going to be the longest consecutive carbon chain. So if I start down here, we've got 1, 2, 3, 4, 5, 6, 7, 8. So I don't think there's any other way I can find more than 8 carbons here. So our parent here is 8. And again, the prefix for 8 is oct. And since it's a parent, we're going to end it in A and E. So that's number 1. Number 2, we've got substituents. So we've got substituents. So we're looking at things that branch off the parent chain. We've got one of them right here. We've got another right here and another right here. And so all of these guys are 1 carbon chain. So all of these guys are methyl groups. We've got a methyl, and a methyl. And so then number 3, after substituents, is to number the chain. So identify the locants. And we do have a couple of options here. So if I started up here at this top carbon and I started numbering 1, 2, 3, we'll go ahead and continue numbering 4, 5, 6, 7, 8. That's one way I could number it. I could also start on the other side, down here, and number it 1, 2, 3, 4, 5, 6, 7, 8. So if I had started with red, my first substituent would come at the 3 position. So this is 3. My second substituent would have come at the 5 position, 5. And then my third would have come at the 6 position. So 3, 5, 6. Whereas if I had numbered in blue, my first substituent would come again at the 3 position. Now my second would come at the 4, and my third would come at the 6. So this would be 3, 4, 6. Again, we have a tie on the first substituent, so we can't utilize that one. Instead, we move to the second, and here 4 comes before 5. So the blue is the correct way to number this. So with that, we've numbered it correctly in the blue. We're going to ignore the red. So go ahead and erase those. Just get rid of all these guys in here. And now we are ready to assemble. So this last one, we're going to assemble the full name. So again, the only substituents we have are methyl groups. And again, we have 3 of them. So we need to specify using that tri as a prefix. First thing's going to come is our locant. So we have 3, 4, 6. And then our substituents, there's trimethyl. And then after substituents, this comes the parent, trimethyl octane. So this would be the correct IUPAC name for that molecule. Okay, so move over to the guy on the right-hand side. Again, we're looking for our parent chain first. So here we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. If we compare that to the ring, which is our other option, we have 1, 2, 3, 4, 5, 6. So because the ring has 6 and this chain has 8, our parent is not the ring. It is instead this 8 carbons because it's more. So again, 8 is octane. And so that is going to be our parent. Now, we need to identify the substituents. So we've got a couple of them. We've got a substituent here. We've got a substituent here. We've got a substituent here. And then we also have the substituent, this guy is another substituent coming off of our parent. So we'll go ahead and identify and name them. So again, we have a 1 carbon chain here. This is a methyl. We have another 1 carbon chain here. This is a methyl. Then we have a 2 carbon chain. This is an ethyl. Then we have a 6-membered cyclic ring structure. So 6 again is hex. So this is hex. Again, because it's a substituent, it'll be hexyl. But because it's also a ring, we have to specify that with the cyclo in front. So this is a cyclohexyl group. Okay, so now once we've done that, we can start numbering. We have 2 ways to number this, or 2 options. We've got 1, 2, 3 versus 1, 2. All right, so the 2 trumps the 3, so we should start numbering it over here. So I'll go ahead and erase these guys. So we've got 1, 2, 3, 4, 5, 6, 7, 8. Now we're ready to assemble. Okay, so now we have a couple options here. We've got a dimethyl, because we have 1, 2 methyls. We've got 1 ethyl, and then we've got a cyclohexyl as our substituent. So again, I had just mentioned that we don't use tert, we don't use sec, we don't use any of these prefixes, the di, tri, etc. But we do use the cyclo as a prefix to help alphabetize. So C becomes before E or M. So this guy's going to come first. It's then going to be followed by the ethyl, because E comes before M, and then we're going to end it with our methyl, or dimethyl. And again, that's because we do not use the di, tri, etc. to alphabetize this. We're going to use the M to alphabetize it. Okay, so it's always going to be locant, followed by substituent. So cyclohexyl comes at the 2 position. So this will be 2 cyclohexyl. That's my first substituent. It's then going to come to the ethyl group. The ethyl is at the 4 position. So -4 ethyl. Again, anytime you separate a number from a letter, you've got to use a dash or a hyphen. And then we have our dimethyl. Because it's dimethyl, you have to say where both of them are. So this is -5,6 dimethyl. Those are all of our substituents, and so then we'll move into the parent. Our parent here is octane. So 2-cyclohexyl, 4-ethyl, 5,6 dimethyl octane. And that is the correct IUPAC name for this structure. Okay, so I have a couple more. Again, the best way to learn this is to do it and to get more and more practice. So we'll take some time here, pause the video, name these guys, and then come back and see the answers. Okay, so we'll go ahead and go over these. So I just want to note down here, we just did this one on the last page, so this was the, how do we number it? 3, 4, 6, so this is 3, 4, 6 trimethyl, and then octane. So my apologies, I don't know how that got replicated. So we'll do 1 and 2, or these first 2 up top. Okay, so again, first step in this is determining where the parent chain is at. So this first one on the left, I think I've got a decane as a parent chain. Yeah. Okay, so if we go, so let's say that we started out here on this carbon, and we kind of 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we went up that way, we would get 9. If instead we went down at that branch, we have 1, 2, 3, 4, 5, 6, and then instead went 7. We'd find, if we kept going, 8, 9, and then 10. So the 10 is going to be the longest chain. Again, if you wanted to say 10 here, that's fine. It's not going to change the structure, because regardless, the first substituent is going to be that methyl group if I go here or if I go here. It's going to be the exact same thing. So it doesn't matter when you come to a branch like that. Okay, so we've got 10 carbons. 10 carbons is decane as a parent. So that's number 1. Number 2, we need to identify our substituents. So we've got a methyl group branching off. So we have a 1 carbon chain here. There's a methyl. We've got a 1, 2 carbon chain here. This guy's an ethyl. And then for the first time, as we come up here, we've got a complex substituent. So we've got a 1, 2, 3 with a methyl branching off of it. So if we wanted to name this formally, this would be, go away. This would be 1, 2, 3. We would name this 1 methyl, because of this guy coming off the 1 position, and then 1 methyl propyl. That would be the name of the substituent. Again, though, hopefully you guys can see that this is one of our common ones. So this is a 1, 2, 3, 4 carbons, so it's a butyl. It's not an isobutyl because it's not a Y. It's not a tert butyl because it's not a chicken foot. So this is actually the sec-butyl group. Sec-butyl. So hopefully you guys could identify that just by looking at it. I'm going to name it with both its common name as well as its IUPAC, its systematic name, with respect to that substituent. Okay, so those are our substituents. Now we need a number. Again, we have 2 options. If we start out here at 1, we don't get to our first substituent until 2, 3, 4, 5, 6. We wouldn't get to this guy until 6. If instead we started over here, we have 1, we get our first substituent at 2. So this is going to be the correct way to number. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we're ready to start assembling. Okay, so a couple things to note. We have an ethyl group, we have a methyl group, and then we have a sec-butyl group. And when we alphabetize, we don't use the sec because it's utilized with a hyphen. Instead, we'll use the B to alphabetize. So this one will come first because B comes before E and M. So that sec-butyl group is at the 5 position. So this is 5 sec-butyl. Then the next one is the ethyl, alphabetically. So this is 4 ethyl. And then the next one, or the last one, is the methyl, 2 methyl. And then we move into the parent, which is octane. Okay, so then we'll move on to the second one. So for this guy, we've got, looking for a parent, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't think that there is anyone else that's going to give us more than 10. Oh, yeah, actually there are. So then we've also got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 2 options here. If we go with the red, no, let's say we go with the black, right? So if we do this guy, I don't want to do that. So this guy, this is what, Chelsea. Okay, so we do this guy. I'm looking at the black, which gave us 10. Then we have 3 substituents, right? So remember that. If instead we go with the red, then we also end up with 4 substituents because we have 1, 2, 3, and then 4. So the red is going to be our parent, again, because if there's a tie, then we want to go with the one that has the most substituents. Because red has 4, black had 3, we're going to go with red as our parent. So then, once we identify that, we can identify our substituents. Also, if we have 10 here, then 10 is decane. So now we can identify our substituents. We've got 2 carbon chain here. We've got a 1 carbon chain here. We've got a 1 carbon chain. And then we've got a complex substituent here. So 1 carbons, we've got a bunch of methyls. So we've got a methyl. We've got a methyl. We've got a 2 carbons. So this guy's an ethyl. And then this guy, again, is our 1, 2, 3. So its complex name would be, if we numbered 1, 2, would be 1 methyl ethyl. So 1 methyl ethyl would be the complex substituent name, but ideally you should see that this is in the shape of a Y. It's in the shape of a Y with 3 carbons in it. So the common name for this is isopropyl. Okay, so now we can start to arrange everything alphabetically. So I'm going to go ahead and delete this guy, or maybe cut it. Though sometime now, it's not very good at cutting things. That's not what I wanted to do. We're going to delete it. We're just going to erase it. You guys know the name of that one. So now we're going to start to arrange everything. We've got a couple of options here. We've got a methyl for alphabetical. We've got an ethyl, and then we've got an iso, right? So the sec we did not use to alphabetize. We used the butyl, but we will use an iso or a cyclo. So we're going to identify this being alphabetized as an I as opposed to a P. So then with that, we've got ethyl first in the alphabet. Oh yeah, we forgot to number. My bad. So if I started down here, I would end up with 1, 2, 3, 4, 5. It would be 5 before I came from my first substituent. Whereas if I started up here, 1, 2, we'd get 2. So the correct numberings is up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now we're ready to assemble. We've got a 3 ethyl. We've got a isopropyl comes next, which is at the 6th position. 6 isopropyl. We've got 1, 2 methyls, and they're at the 2 and the 4. So this is 2, 4 dimethyl. And then our parent is decane. What did I... Man, this other one, this is not good. I'm sure you've already gotten mad at me and yelled at the screen at this point. This parent over here was also decane, but so for some reason I called it octane. So my bad. We'll erase that. This is not octane. This is decane. And so, yes, you probably have already seen, probably have started emailing me about how I was wrong on that. But my bad. Okay, so we have 3 ethyl, 6 isopropyl, 2,4-dimethyl decane for final answer for this guy. And then you guys saw it was the 5-sec-butyl for ethyl 2-methyl decane for the first one. Okay, so last little bit with respect to this, and then I'm going to upload this. The other thing that we can do, or the other types of problems that you will be given, is given a name, they're going to want you to draw the bond line structure for the compound. Okay, so I'm going to go through an example, and I'm going to have you do 2 on your own. So here, we have been given the name of this compound, and they want us to draw the actual structure. Okay, so whenever I start any type of problem like this, I always start with the parent, which for this guy is pentane, and I will just draw a pentane, right? So pentane is 5 carbons, and so I'm just going to draw via bond line structure 1, 2, 3, 4, 1, 2, 3, 4, 5. I hate that. I'm going to do that again. 1, 2, 3, 4, 5, right? So we've got 1, 2, 3, 4, 5, right? That's going to start it. Now, with respect to drawing these guys, I can number this however I want, right? So I could start by numbering this guy as 1, or I could start by numbering this guy as 1. It does not matter regardless. So I'm going to go ahead, just to be consistent, I'm going to start on the left, because we always read from left to right. So we've got a 1, a 2, a 3, a 4, and a 5. So usually I'll do the parent, and then I'll go ahead and number the parent. And then I'm going to attach substituents to it, right? So they tell us here that at the 3 position, we get an isopropyl group, and you guys should ideally know that an isopropyl looks like a Y. And then it says at the 2,4 position, so 2,4 position, we get a methyl. And a methyl is just a line, it's just 1 carbon. So we'll go ahead and draw that at the 2,4 position. So the 2 position, remember with bond line structure, we're trying to denote tetrahedral structure. So if I've already got my 1 and 2, then my methyl group I'm going to just have pointing up. Same thing with the 4 position. I've already got 1, 2. These guys are in the plane, so then I'll have this guy pointing up as well. And then at the 3 position, we get that isopropyl group. I'm just going to have a Y coming down at the 3 position. So this is 3 isopropyl 2,4-dimethyl pentane, right? So again, I would go with parent first. So draw the parent, and then number the parent, and then attach the various substituents. So go ahead and try this one. We've got a 4-ethyl 2-methyl hexane, as well as a 1,1,2,2 tetramethyl cyclopropane. So go ahead and pause the video, work on these, and then come back. Okay, so we'll go ahead and go over these. Again, for the first one, I'm going to start with the parent, which is hexane. So I'm going to try to draw a nice, beautiful hexane molecule. So 1, 2, 3, 4, 5, 6. We'll go ahead and highlight those guys. We've got 1, 2, 3, 4, 5, 6. I'm going to go ahead and start numbering from the left-hand side. So we've got 1, 2, 3, 4, 5, and then 6. After I've numbered, I'm going to add whatever substituents they tell me to. So I've got a 4-ethyl. So I'll go ahead at the 4 position. I'll draw an ethyl group. So an ethyl is a 1-carbon, 2-carbon chain. And then we've got a 2-methyl. So at the 2 position, I'll just draw a methyl group, and I'll make that the same color. Okay, so this is 4-ethyl 2-methyl hexane. So then the last one is a little bit more maybe difficult, I don't know. So our parent here is a cyclopropane. Cyclopropane is 3 carbons, so it's a 3-carbon ring. So essentially, we're just going to draw a triangle. So this is our 1, 2, 3 carbons. Again, we can start numbering this however we want to. So I'm going to go ahead and say 1, 2, 3. And then we have tetramethyl, right? So we have 2 methyl groups at the 1 position. We have 1, 1. So 2 of them are here, and then 2 of them are here. So I'm going to go ahead at the 1 position. I'm going to draw 1 methyl group, and then another methyl group. And then at the 2 position, I'm going to do the exact same thing, where I draw 1 methyl and 1 methyl. And that is it. That is what a 1,1,2,2 tetramethyl cyclopropane would look like. Okay, so I'm going to go ahead and upload this now. It's kind of long at this point with the problems in it. I'm going to say that this is the Tuesday lecture, just because it's been a while and everyone was super lost the last time, or most people looked fairly confused when we went over this right before we left for break. So this will be the assignment for Tuesday, and then I'll upload new material on Thursday. But again, I would start doing the homework as soon as possible. And don't forget, there's going to be a quiz that is associated with this. It will not cover that much like actual material. I'm looking instead of you guys kind of giving me an assessment on how you thought the video was, etc., or how you or what was confusing, etc. So you'll see. Just go through it. You'll get 2 attempts. Email me if you guys have questions, and wash your hands. Stay safe. Okay, bye.